Hello friends, myself Vipul Patel. Welcome to my channel Smart Learning. In this session, we are going to discuss on Static Scherbius Drive. This drive provides the speed control of wound rotor motor below synchronous speed. The portion of rotor AC power is converted into DC by a diode bridge. The control rectifier works as inverter and converts the DC power bank into AC and feeds it back to the AC source. This drive has the ability of flow the power both in the positive as well as the negative direction of the injected voltage. This increases the operating condition of the drive. The feedback power is controlled by controlling the inverter counter EMF Vd2, which is controlled by controlling the inverter firing angle. This Vd2 is shortly we see in the figure. The DC link inverter reduces the ripple in DC link current ID. The slip power of the drive is fed back to the source, due to which the efficiency of the drive increases. In this figure, you can see the drive. In that, you can see this is the induction motor, these are the supply voltages, this is the transformer, these are the thyristor, these are the bridge. And the Vd1, this Vd1 is here and Vd2 is here. This is the ID current. The drive input power is the difference of the DC input power and the power feedback. The reactive input power is the sum of the motor and input reactive power. Thus, the drive has poor power factor throughout the range of its operation. Now, Vd1, that is voltage Vd1 equal to 3 into under root 6 by pi into SV upon N. This is equation 1. Consider here. And Vd2 equal to 3 into under root 6 upon pi into V upon M into cos alpha. Consider this equation 2. In this equation, alpha is the inverter firing angle, and N and M are the respectively the stator to the rotor turn ratio of the motor and source side to convert side turns ratio of the transformer. The neglected drop across the inductor, that is Vd1 plus Vd2 equal to 0. Substituting the equation 1 and 2 in the above equation. So we get this is the value of Vd1, Vd2. Finally, we get the S upon N equal to minus cos alpha upon M. Finally, the S, that is slip, equal to minus A cos alpha. Consider this equation is third equation. In that equation, this A equal to N by M, the ratio of Nm. The maximum value of alpha is restricted to 165 degree for safe commutation of inverter thyristor. The slip can be controlled from 0 to 0.966 alpha when alpha is changed from 90 degree to 165 degree. The appropriate speed range can be obtained by choosing the appropriate value of alpha. The transformer is used to match the voltage from Vd1 and Vd2. At the lowest speed required from the drive, Vd1 will have the maximum value Vd1m, and it's given by Vd1m equal to Vs max upon N, where Sm is the value of slip at the lowest speed. If alpha is restricted to 165 degree and M is chosen such that the inverter voltage has a value Vd1 M when alpha is 165 degree. That is, you can see in the equation. From that, M can be equal to minus 0.966 into N upon S max. The value of M determines the highest firing angle at the lower motor speed. It also gives the highest firing angle and the lowest reactive power at the lowest speed. Consider the circuit of the motor which is neglecting the magnetizing branch. When referred to DC-link, the resistance SRS plus RR will be 2SRS plus RR. This equation you can see in the next diagram. This gives the equivalent circuit of the drive where Vd1, Vd2 are given and Rd is the resistance of the DC-link inductor. In this diagram, you can see all the components. This circuit diagram is equivalent circuit of motor and this diagram is equivalent circuit of drive. In that, you can see this is resistive and this is reactive component and these are the resistance, total resistance of drive. So, from the previous diagram, M equal to finally 0.966 minus 0.966 N upon S max. If rotor copper loss is neglected, then the Pg, that is copper loss, that is equal to Pd2 into Id upon S, and the equation of torque, that is T equal to Pg upon Wms. Finally, we get Vd2 into Id upon SWMS. Consider this equation number 6. So the nature of the speed torque curve is shown in figure below. Here you can see the characteristic of speed versus torque. The drive has application in pump drive which require the speed control in narrow range only. The drive is widely used in medium and high power fan and pump drives because of high efficiency and low cost. Now, operating modes of this drive. First mode is sub-synchronous motoring. In this mode of operation, the slip and torque both are positive and hence the injected voltage is in phase with the rotor current. The power flows into the stator and feedback into the rotor circuit. Second mode is supersynchronous motoring, in that when the speed of the motor is above the synchronous speed, then the slip is negative. Thus, the voltage and current are out of phase with each other. The power feeds into the rotor from the drive circuit along with input power flowing into the stator. Third mode is sub-synchronous generating. For sub-synchronous speed, the torque is required to be positive. Although the slip is positive, the power is fed into the rotor through the slip ring. And the last mode is super synchronous generating. When the speed of motor above the synchronous speed, then the slip and torque becomes negative. Thus, the injected voltage is in phase the rotor. The mechanical power is injected by the shaft and the output power is obtained from the stator and rotor circuit. This is all about operating modes. Thank you for watching this video.